Hi and welcome to this video.
Who the hell are you?
My name is Jan-Hendrik and in this video I would like to cover measures of dispersion in R, and I would like to cover the full theory about that topic. Let's see what I planned for today's video. First, I would like to go into the usual measures of dispersion that are the variance, the standard deviation, and the coefficient of variation or variation coefficient. And then I would like to discuss a more robust one, the interquartile distance. And I would like to talk about skewness and kurtosis, which are the third and the fourth moment of a distribution. The mean is the first, and of course the variance or standard deviation are the second. What is that all for? In all journal articles you will typically find a table like this, Descriptive Statistics, and many researchers grant a first view into their data by making such a table. It's typically the first table in the result section of an empirical article. And there you will find for all the variables the number of observations, the mean. I just did another video about measures of central tendency, and for example the standard deviation, just like here. So measures of dispersion. Many researchers show more than we see here. Often skewness and kurtosis are both shown too. Of course that all comes out of statistics software or programs. Just like here, this one is German by the way. Nevertheless, arithmetic mean is given here, the median, the minimum, the maximum, and for today the standard deviation and the variation coefficient, and the skewness and the excess kurtosis. About the difference between kurtosis and excess kurtosis, we're going to discuss that later. I prepared a little data for our video today, and that is income data. Income data for a very small population. Here we have 9 observations, 9 persons. One with 22,000 euro income, one with 24,000 euro income, one with 25, and so on and so forth. And the rich guy to our right has an income of 105,000 euro.
What's your game, Mr. Bond?
My game?
You didn't come here to play golf.
And of course, measures of dispersion measure the dispersion of the income in this case. So, if we plot that into a strip chart is a chart with one axis, the x-axis, we will see, so this is exactly the income that we just see on top here, and we see that those points are close together, but those are quite dispersed. So a measure of dispersion tells us about the dispersion. Down here, this is another data set, they are closer together. So I would expect that a measure of dispersion will be 0 if they are all in one point, and it will be quite large if they are very dispersed. Let's go into R and let's see how that is implemented. Okay, I've just arrived in our studio, and the first thing I always do is to open a new script file and to give it a beautiful headline. 1, 2, 3, 4, 5 hashtags, measures of dispersion. And of course the first thing that we need is some data. I manually input the data here. I give it the name vector income, so we all know what that is, vector income. And I assign a vector to it using the C command, which stands for combine. Combining a vector, we have 22,000, we have 24,000, we have 25,000, we have 30,000, we have 34,000, we have 50,000, We have 65,000. Nope. We have 70,000. And we have the rich guy 105,000. I just run this line, and here on the right hand side in the environment I see the vector income, which is a numerical vector 1 to 9 items or elements, and there are all my elements. So this is my data. And the first measure of dispersion is the variance. Okay, so the command for the variance is simple. It's var, and of course I have to hand over our vector income. And I just run this and I get this enormously large number here, 790,194,444 euro squared. What? Euro squared? Well, later on we're going to discuss why it's euro squared, but it's a squared number here. Accordingly, it is very, very large. A bit better, of course, is the standard deviation. Let's go into that. And the standard deviation has the command SD. Of course, I have to hand over the vector income. And I just run it, and there it is. It is 28,110. So, roughly speaking, the average deviation from the mean. What was the mean again? The arithmetic mean, of course. I just do it in the console. Vector income. The mean was 47,222, so that's the average of those 9 persons. But on average, they deviate from that mean of 28,110. That's how we can interpret this. By the way, the standard deviation is, of course, the square root of the variance. Well, and the coefficient of variation. There is no command for it, but the coefficient of variation is just a standard distribution. Accordingly, we can use the standard distribution that we have already used and divided by the mean that we have also already calculated. And there it is 0.59. So it's a 59% deviation that we see here from the mean on average. So this is how to interpret this one. Last but not least, I would like to introduce the inter-quartile range, which is robust, a robust measure. It will not be biased by statistical outliers. The command is IQR, and please keep in mind that these are capital letters. That is very important. IQR in capital letters, and of course we hand over the vector income again. Let's run this, and the interquartile range is 40,000 euro. That was it about the measures of dispersion. Now let's have a look at the skewness and the kurtosis. We still need that one. Nevertheless, skewness and kurtosis are not implemented in our base. Accordingly, we will need some package for that. And the package we have to install, let's go into that, skewness and kurtosis. We need to install the package that is called moments. Let's run this. Just takes a few seconds, and there it is. Now we can use it, but since we have never to install it again, we make a command out of this: if not yet done. Install it. So if you share your code with your colleagues or students or whatsoever, if they haven't yet installed, they see it, okay, if not yet done, they can take out of the command line this command and run it and put it back. So it's easy as that, but what we always have to do is to run the library moments. Keep in mind, here it is in quotation marks and here it is without quotation marks. I run the library and now I can access the skewness, and the command is skewness, of course. I hand over the vector income and I get a skewness of 0.97. It's positively skewed, or in other words, we have a more dense part on the left-hand side and a more spread part on the right-hand side of our distribution. Do we have a kurtosis? The command, of course, is kurtosis. And I hand over the vector, and there's the kurtosis. By the way, this is Pearson's kurtosis. It is not the excess kurtosis. We can also calculate the excess kurtosis. Of course, we just need the kurtosis for that. And we subtract 3, and then we have the excess kurtosis here, which is 2.83. Okay, let's have a little look into the theory to those of you who are not so much into what we have just calculated.
All right, bonus round.
Well, was our last chart, and I already mentioned that we want to know about the distribution or dispersion of these points. If they are largely dispersed, our measure of dispersion should be large. If they're densely dispersed, our measure of dispersion should be small. And if they're all in one point, it should be 0. So this is what we want to achieve. Now, the first idea that comes into our mind, of course, if they are dispersed around the arithmetic mean, of course, we can calculate the distances. Now, if we look at this point, the distance between this point and the arithmetic mean here is just this line. I have put this line here on top. The distance between this point and the arithmetic mean is exactly this line here. So we take the x value, or the income in this case, minus the average income. Okay. But if we look down here, maybe on this point, the distance between this point and the arithmetic mean is this line, but the length of this line is negative. Why is it negative? If we again use the same formula, like taking the x value, taking the observed income, and subtract the larger arithmetic mean, we will get some negative distance. We have to keep that in mind. Because now, if we want to know about dispersion, the next idea would be to add them all up and maybe to take an average distance here. But since these are all negative and these are all positive, they would average out, and the average distance here would be 0. That's exactly a property of the arithmetic mean. So all the distances average out. We always get 0. So this cannot be our objective to do it like that. What else could we do? We could take the absolute values. So these are already positive and these are negative, but if we take the absolute value, we turn around their sign and do as if they were positive. Indeed, there is a measure of dispersion that is calculated like this. The name of this measure is the mean absolute distance. For example, in Excel, you will find a formula that does exactly that. Nevertheless, the mean absolute distance is not so widely used. I will just show on the next slide why that is the case. What is more widespread, let's put it like that, is to take the square of those distances. So to square them. If we square a negative value, it becomes positive. And if we square a positive value, it stays positive. So they get all be positive then. So the squared values here is the way we should go. Well, if we want to calculate these values, we can use this formula for the variance. Typically, the formula for the variance is written like this. It's an as. We indicate the variable, it's x, and it is squared because the variance is always squared. Of course, this 1 divided by n makes the sum become an average, so we are going to average everything. That's why we divide by the number of observations. N is 1, 2, 3, 4, 5, 6, 7, 8, 9. So n will be 9. It's the number of observations. And here we have a sum sign, right? And the sum sign sums all xi, I is the index, and the index is counting from 1 to n. 1, 2, 3, 4, 5 up to 9. So we take x1 minus the average, x2 minus the average, and so on and so forth, and they all get squared. Well, if we put this into practice, of course, we take 22,000 minus the average, 47,200, and we have to square it. And we do this for all the elements up to the rich guy here, and divide all that by 9. And I have left away the zeros here to make it a bit more clear. Nevertheless, if we introduce those zeros again, we have 790,194,444. Quite a large number, and it is in euros squared, because we still are in the world of squared numbers here. If we then take the root out of that, we will receive some 28,110. So the standard deviation, written just like Sx in this case, is the root of the variance, and that is 28,111. It can be interpreted as the average distance to the mean of all those observations. And standardizing that with the mean, just like it is shown here, will give our variation coefficient, and that was 0.595, 59% deviation from the mean on average. Why now is the squared value, just here squaring and here squaring, better than taking the absolute value? I will show you. So if we understand the absolute value as a function, absolute value function, and the squared value as a function again, we have an absolute value function that looks like this. Why does it look like this? Well, we have all the numbers on the x-axis, but the negative numbers are getting turned positive. Accordingly, a minus, let's say 4, minus 4, it's getting positive 4. So minus 5 is getting positive 5. So it's linear, it's going down, and here it turns around, and it goes up again because the positive 5 will be a positive 5 here too. So that's the absolute value function. This absolute value function has a big downside, because in the minimum it is not differentiable. And we want to differentiate. Let's make an example. For example, we need something like the minimum variance portfolio in portfolio theory, the portfolio that bears the least risk. Of course, we need to make an optimization. We are looking for the minimum. So we have to derive it, and we have to set it 0. This one can't be derived. So taking the absolute value function will lead into pretty much nothing because we can't handle it. Accordingly, the squared value function, minus 5 becomes 25, minus 4 becomes 16, minus 3 becomes 9. And on the right hand side, 3 becomes 9, 4 becomes 16, 5 becomes 25, and so on and so forth. So the squared value function has a better property here, since it has this beautiful curvature and it is perfectly differentiable on all in all spots, in all values. Well, there is a beautiful alternative formula for the variance, and I just want to show you, and I want to also show you the how to derive it, because that must be understood more or less. Well, this is the formula that we already know. Okay, this is the formula that we already know, and well, let's take a look into this. So if we square such a bracket, this is what we call the binomial formula, right? And we can apply the binomial formula here. I just do that. To make my life a little easier, I just write the I, which means summing all i's. You know what I mean, it's the same as here. And now, of course, I apply the binomial formula. So, I have to square xi. I take minus 2 times xi x bar, which is x mean, plus x bar squared. So this is just the application of the binomial formula. Now we see that we have a sum sign here, and we have not a sum sign but a minus, which is also additive, and a plus here. So we have a sum of sums. And of course, a sum of sums, it doesn't matter in which dimension I sum up first, so I can also distribute the sum sign to all those terms, but of course I will need some brackets to do so. So 1 divided by n, large brackets, and now I use the sum sign for each individual term, so I use the sum sign for xi squared. Now of course minus the sum sign for 2 xi x bar, and plus the sum sign for x bar squared. So it's just distributing the sum sign to all 3 individual terms. That's pretty much allowed. It's just a sum of sums. Okay, now I have to make a little excursus, and I'm going to write this excursus here.
Someone touched my board. Oh God, my board.
And the excursus is about the handling of the sum sign. Some of you might already know, nevertheless, I'm going to repeat this. So if we have a formula just like a plus b xi, how can we handle this formula? The first thing is that we are going to add up the a n times, because I is counting from 1 to n, right? I just complete that. I is counting from 1 to n. So we add up the a n times. We can take it out of the sum sign by just multiplying it with n. So n times a plus the sum sign across all I, b, xi. Well, and the b, of course, is multiplied with xi. we can also take it out of the sum sign. So we have NA plus B times the sum across all xi. So this is very important to know how to handle additively connected variables and multiplicatively connected variables.
Leonard!
Hey, what's the matter?
My equations. Someone's tampered with my equations.
Are you sure?
Of course I'm sure. Look at the beta function of quantum chromodynamics. The sign's been changed.
Oh, yeah. But doesn't that fix the problem you've been having?
Are you insane? Are you out of your mind? Hey, look, that fixes the problem I've been having.
And we're going to apply this to our formula here now. And just make it a bit more, well, I don't know if it's beautiful. Now, I'm going to use it now. 1 divided by n, of course this is still equivalent. The sum sign across all I, we still stick with this one, but the middle one here, we have the 2, and of course we can take out the 2 out of the sum sign, and we have the x squared that we can also take out of the sum sign because it has no index, and we stick with the sum sign across all I, xi, and plus sum sign across all I, x bar squared. Alright, so we applied what we have learned here to the formula, and that helps us a lot. And now we're going to solve the brackets just by multiplying out the 1 divided by n. And we will have, of course, 1 divided by n, the first sum sign, minus 1 divided by n, or let me put this in front, x squared, I put it here, the second sum sign, and of course 1 divided by n, the third sum sign. Well, and now we have beautiful properties here, because if we look at this first part here, this is 1 divided by n and a sum. This is an average of all xi's squared. So we have x squared bar, because it's the average of all xi squared. Now we have this minus 2x sign. I just keep that 1. But here it's again an average, 1 divided by n and the sum across all x. This is x bar. Oh, I forgot the bar here. This is x bar again. And here, this is of course again an average of x bar squared. So, since this is also x bar squared, we have x squared bar minus x bar squared. And this is the alternative formula for our variance that you quite often find in the textbooks. And now you know where it comes from. So you have to square all x's, take the average, and subtract the average squared. That's it. Quite easy to memorize. Nevertheless, to me, this one pleases me more because it has the full idea of the variance in. Nevertheless, those of you who can handle the formula better, just use it. It's the same. Now let us talk about the interquartile distance. The quartiles are fourth. So if you divide your data in fourth, let's say parts or 4 quartiles, which are all of the same size, so 25% of the data here, 25% here, 25% here, 25% here. The values in between those fourth parts are called quartiles. First quartile, second quartile, and third quartile. The first quartile here is the value where 25% of the data is below and 75% of the data is above. The second quartile is exactly the median, because 50% is lower and 50% is higher. And the third quartile is where 75% is lower and 25% is higher. The interquartile distance is now defined as the difference between the third quartile and the first quartile. So exactly that distance between those points where 25% are lower, 50 are in between, and 25 are higher. So that's the definition of the interquartile distance. The interquartile distance is quite robust against statistical outliers, because statistical outliers, just like the rich guy here on the right hand side with his 105,000 income, even if that guy would become a lot richer, the quartiles would not be affected. Accordingly, it is robust against outliers. The variance or the standard deviation are not, because they would get changed if the rich guy is getting richer and richer or is replaced by an even more wealthy man. Now, this skewness tells us about, let's say, the shape of our distribution. We see here with the dotted line, we see a typical normal distribution. This is a normal distribution. If we now look at the red line, which is quite steep here, it goes steeply upwards and then goes down rather flat. This is a positively skewed distribution. While the black line here, which is steep to the right hand side, is called negatively skewed. The Greek letter that we see here is the mu, and the mu is the measure for skewness. And if the skewness or the mu is positive, we speak of a positively skewed distribution, and if it is negative, we speak of a negatively skewed distribution. Let's see how that is defined. The skewness is defined or called the third momentum of a distribution because it is calculated in the power of 3. Let's see what happens here. The mu is defined as the average of all distances above the fraction line here. These are the distances we already know, and those distances are standardized by, let's say, the mean distance, the standard distribution, because it is the mean distance, the average distance to the mean of all those observations. Well, and if now, what happens here? Now, if the distance of a certain observation is exactly as long as the average distance, of course, the fraction becomes 1. If it is shorter, the fraction will become 0 point something, and if it is longer, of course, the fraction will become 1 point something or even higher. Now, so we standardize all those distances with the average distance, with the standard deviation here, and then they get they have an exponent of 3. They will be calculated in the power of 3, and taking them in the power of 3 means that the sign is preserved, because the distance can also be negative. We have already seen that in the beginning. So if it is negative, even in the power of 3, it is still negative. If it is positive, it is still positive. So, what happens? Observations that are very far away from the mean, they will have a lot of weight in this average. Those that are very close to the mean, they will have only little weight in this average. Now, let's go into our distribution and then we see what happens. Here's the distribution again, and we look at this positively skewed distribution, the red one. Here we have the median, so half of the observations are left to the median and half of the observations are right to the median. But of course the arithmetic mean is right to the median. Why is that the case? Because we have the rich guys here and those that are very far away from the middle pull the arithmetic mean to the right. So we have more observations to the left-hand side of the arithmetic mean than we have observations left-hand side than we have to the right-hand side. So here are fewer observations and here are more observations. But the observations here to the left, they are very close to the arithmetic mean. I have just introduced here this arrow that covers exactly one standard deviation in both directions, to the left one and to the right one. And if we now look that we have many observations that are lying under this arrow, accordingly the fraction for them will be below 1. And in the power of 3 they will even be smaller. So more observations left to the arithmetic mean, but smaller distances, and the smaller distances get even smaller if they are taken in the power of 3. To the right hand side we again see one standard deviation, but we only see a few points and other points are far away. And those points, those observations being far away from the mean, now get a very large weight because they are positive, they are far above 1 in the fraction, and in the power of 3 they get even larger. So accordingly the mu here will get many very small negative values and a few very large positive ones, and that's why this distribution is called positively skewed. The fourth momentum of the distribution is the kurtosis. The kurtosis tells us a bit about the shape again of our distribution. Let's say about the tiptedness. So again, the dotted line is a normal distribution here. And if we have one of those very high peaks in the middle, we call this leptokurtic. The peak in the middle also comes with quite fat tails, because if we follow it, we see here on the end that the tail of this distribution, to the right as well as to the left, is a lot more fat than the normal distribution. This is, for example, very important in capital market research, because in capital market we have leptokurtic distributions. Why that? Because very strong movements of the stock market are more often than normal distribution would predict. And that nothing happens at the stock exchange, nothing happens to the stock price, is also quite more often than normal distribution would predict. But low changes of stock prices are fewer. So here we are above normal in this area here, then we go below normal, and then we go above normal again. So this is what we typically have in stock price data. The platykurtic distribution here, of course, has a flat peak. It has a flat peak and it goes far below the normal distribution here. How is all that defined? Pearson's kurtosis is defined as omega here. Omega, again, is an average, 1 divided by the number of observations, and we have a large sum sign across something. Inside the brackets here, we see again the distances that can be positive, that can be negative, that can be rather long or rather short. And they are again standardized by the average distance, defined as the standard deviation. So, a distance smaller than standard deviation is below, above -1 or below 1, and distances above the standard deviation will have a fraction that is larger than 1 or below -1. Then, taking them in the power of 4 will again turn all signs positive. So, in the power of 4 will turn all signs positive. Now, typically today, we use the excess kurtosis, and the excess kurtosis is simply it's gamma. Gamma is omega minus 3. Why 3? Because 3 is the kurtosis of a normal distribution. So we have an orientation. We reflect the kurtosis with the kurtosis of the normal distribution. Let's have a look at that. Here again we have this fat tail or leptokurtic distribution, and what's typical for a leptokurtic distribution, it has more observations in the tails than we would expect from normal distributions. So they are all far away. They all exceed the standard deviation. And if they all exceed the standard deviation, of course, omega becomes quite large and gamma becomes larger too. Accordingly, a leptokurtic distribution with fat tails has this positive value of gamma here. That was it for today. Thank you very much for watching this video, and see you in the next video.
No! No! Wait! Don't leave me out here! Please! Don't leave me!